Good evening all. It gives me a great pleasure to introduce today's speaker, Professor P.P. Mujumdar. Professor Mujumdar is presently a professor in the Department of Civil Engineering at IISER. He is also the chairman of Interdisciplinary Center for Water Research and has an associate faculty position in the Center for Earth Sciences at IISER Bangalore. Professor Mujumdar is a hydrologist. His area of specialization is water resources with a focus on climate change impacts on hydrology, statistical downscaling of global climate model outputs, urban flooding, planning and operation of large-scale water resource system. He has close to 100 peer-reviewed publications and numerous book chapters. He is one of the exemplary academicians who actively engage themselves in applying the scientific understanding to address issues of societal relevance. This commitment is reflected in his engagement in a number of state and national committees that tries to deal with urban flooding and operational hurdles of water resources in India. He has served as the chairman of Water Resource Management section of the International Association for Hydro-Environment Engineering and Research and as a reviewer for the Assessment Report 5 of the IPCC. Professor Mujumdar received prestigious recognition from both national and international organizations, Alexander von Humboldt Medal of the European Geosciences Union, the Distinguished Visiting Professor Fellowship of the Royal Academy of Engineering, UK, J.C. Bosch National Fellowship, Fellowship of IISc, INSA, and INAE, to name a few. Without further ado, let us welcome Professor P.P. Mujumdar to the Institute Colloquium of IISER Pune today. Professor Mujumdar.
Thank you very much for that introduction, and it's a great privilege for me and pleasure to be here in IISER, and I thank the Center for Earth Sciences in particular and IISER in general, but mainly Shyam, whom I know for a long time. So thank you all for coming for this presentation, and I alert you that some of you would have already listened to this presentation earlier, so please pardon me if things sound repeating. So essentially what I am going to talk about in this colloquium is about how the human interventions are changing the hydrology at several scales, including the point scales in as much as the rainfall is concerned, then the other hydrologic variables such as stream flow, evapotranspiration, which govern the water requirements, water availability as well as water demands. So when we are talking about hydrologic processes, the first aspect that we need to know are the catchment scale processes that take place. Typically, the question is what happens to rain once it falls on the ground. That is the type of questions that the hydrologists will be interested in. So, as you can imagine, as the rain falls, the first level of hydrologic process starts is with respect to evaporation itself. As it is falling, there is a evaporation. Then there is a interception. Because of the vegetation, because of the man-made structures, etc., the rainwater will be intercepted. Then part of it comes and falls on the ground. As it falls on the ground, depending on the soil conditions, the type of soil, etc., part of it comes as runoff and then joins the streams, and part of it also goes down as infiltration and subsequently may join as groundwater, or it may also evapotranspirate. When we say evapotranspirate, it includes the bare soil evaporation that happens from the soil as well as from the water bodies, as well as the transpiration that happens from the vegetation. So, both these together we call it as evapotranspiration. So, the question now is how are these interconnected at different scales? As you can imagine, the precipitation, depending on the type of precipitation, it can happen very quickly. For example, the convective type of precipitation, cumulus precipitation, it happens at a very small time scale, and then you also have other processes. So, let us start with the hydrologic processes that happen at different scales. As I said, as the rain falls, you have the canopy evaporation, there is a transpiration, then part of it goes down as deep percolation, This will depend on the soil type, the soil condition as well as the vegetation type. What goes down may come as through flow between the soil surface and the saturated flow, which is the groundwater. There is a horizontal flow that also takes place. That is the unsaturated zone, and then part of it may also go and join the groundwater storage, which is called as the recharge. Now, the runoff that starts from the rainfall may start because the soil gets saturated, that is called as a saturated overland flow. It may get saturated from above because the soil rain is happening from above, or it may get saturated from below because of the saturation from the groundwater side. That overland flow subsequently becomes a runoff, and then it may join water bodies such as rivers, ponds, etc., which subsequently may join the ocean. So, these are broadly the processes, but we will be essentially interested in evaporation and transpiration, and of course, the rainfall, which is the main forcing here. The runoff, which contributes to the stream, that dictates the availability of water, and then the recharge, which also joins the groundwater. So, when you look at different hydrologic processes, these will typically occur at different space time scales, and it is quite interesting. This is got from Sivapalan's paper, classic paper on scale issues. If you look at just the precipitation processes, you have cumulus convection, which happens at about 100 meter scale and so on, then thunderstorms, then these are cold fronts, and then the fronts, etc. So, this is a length scale. Similarly, you have, once the rain falls on the ground, you have excess overland flow, that is infiltration excess as well as saturation excess. These happen at these scales, but what is also important to notice is the time scales. For example, the convective type of rainfall may happen very quickly, maybe of the order of half an hour and so on. And as you progress along this, when you look at the groundwater flow, these can happen over hundreds of years, and that is the range of scale that we are talking about, both on space as well as on time. It is an order of about 8 orders of scale difference that you see. Now, the shaded region here, that shows the variability typically, and what is of interest here is that if you simply take the ratio, characteristic length and time scales, that seems to remain constant for a particular process, and that is what is interesting. And this is done both analytically as well as a large number of observations. So, the space time scales that we talk about in various processes, that becomes important. Now, that is about the scales. Now, as we are aware, in the current era where human signatures are felt in most of the natural processes, much more so on the water systems, you can see these type of signatures that we see on the water systems. First, if you look at the global scale climate change, the anthropogenic climate change, there used to be a doubt or debate on whether the climate change that we are seeing, in fact, the debate still goes on, is because of anthropogenic change or it is part of the natural cycle. But that apart, there are global signatures that will be felt on the regional hydrology, and these will include changes in the patterns of precipitation, stream flow, all of these processes because of the global climate change, and that can be anthropogenic climate change. On top of that, if you look at larger scales, for example, those who are from peninsular region, you know what is happening in Kaveri basin, or from the Himalayan region, what is happening on the Ganga basin. Over a period of time, over the last about 4 to 5 decades, the land use has changed significantly. It has become mainly agriculture, from forest and scrub forest, etc. It has become agriculture, and urbanization is also growing. Now, these will include changes in stream flow, evapotranspiration, and all other variables. Then there are human constructions, for example, dams, hydraulic structures, etc. These are the constructions on the flow regimes, and they alter the flow regime. Then there is also a large scale irrigation, interbasin transfer of water, etc. But what is also of importance is this kind of situation you see everywhere. That is an over exploitation of groundwater, mainly for agricultural purposes. These have led to shrinkages in the groundwater levels because of the excessive pumping. What is also of importance is the way our cities are growing. There is hardly any space for additional water related infrastructure. And we are seeing floods in cities every year. Almost every city goes through floods, and there is hardly any place that is available for the infrastructure. So, these are the human signatures that will be felt at different scales and on different processes on the water systems. Now, as I mentioned about the runoff, you look at these two types of catchments, the same intensity of rainfall happening here and here will produce a different response. This response from such a catchment will be slow, smooth and uniform in some sense, whereas as soon as the rain falls here, it has to convert itself into runoff, because there is no opportunity or time for it to evaporate nor to go down. And therefore, the challenge here is how quickly it runs off and how quickly you are able to drain, whereas the challenge there is this is a much smoother watershed, and therefore, it behaves much more smoothly, less of challenges in dealing with this. The evapotranspiration that I talked about essentially governs how much of water is required by the vegetation. So, if you imagine there is a large irrigated area and then a large agriculture area, for example, how much of water demand or how much of water it takes up, that is governed by the evapotranspiration. And the evapotranspiration is governed by all of these, for example, the air temperature, radiation, and then the wind speed, humidity, etc. These are the climatic factors, but apart from that, there are also other factors such as type of vegetation, season of vegetation, crop growth, etc. So, on one side you are talking about the runoff which is generated based on the soil conditions, on the other you are also looking at the evapotranspirative demands. The runoff joins the stream flow and therefore governs in some sense the water availability, the evapotranspiration governs the water demands, and this is what we start looking at. Now, as hydrologists, we understand the processes in their quantitative measures at all scales. For example, for a given rainfall happening at a particular area, small scale here, depending on the type of soil, depending on the condition of soil, depending on the land use pattern, the type of vegetation, depending on the climate, how all of these processes are generated is what we understand at these small scales. In the distributed hydrologic models, remember here, because the hydrologic processes are extremely heterogeneous, as intuitively you will know, what is happening in IISER Pune when a rain happens here, just about 10 kilometers away, the conditions may be much different. There is a very significant spatial variability as well as the heterogeneities on the soils and the land use conditions, etc. And therefore, we need to look at these processes at very small scales. In the distributed models, we divide this area into small elements. At every element, we simulate all these processes and bring it down to the point of interest. Let us say you are looking at a small river basin or stream and you bring it up to this point. When you are doing so, you not only look at the surface, but you also look into the soil and then see how the soil moisture behaves below the ground and then simulate those also. Similarly, we also have the groundwater models, how the groundwater flows. That depends again on the aquifer characteristics, and typically we use the transmissivity and the specific yield as the parameters which can be estimated. This is just a two-dimensional type of groundwater model. Essentially what it does is it applies the continuity. That means there is a flux that is coming in and then there is a discharge that is going out and there is a pumping and recharge. That is all that is done, but that is done at a very small scales. And when we are talking about groundwater models, those who are aware of these geologic conditions, etc., you may have dikes, and therefore, the flow is not crossing across those dikes. So, you specify the boundary conditions accordingly, or you may have rivers on the stream and those dictate certain other boundary conditions. So, typically we use the finite element type of methods and then specify the boundary conditions according to the actual field conditions and then solve that. Then we also have the water quality issues. You imagine there is a stream that is going on in flowing in a pristine condition, and then there is a shock in terms of the industrial or municipal effluent that is coming here. The first level of water quality, namely the dissolved oxygen. If the water quality is good, the dissolved oxygen is at near saturation level. That's the first level of water quality. Now, the moment this shock is received, the biochemical oxygen demand starts increasing, it shoots up, because of which the dissolved oxygen starts coming down. If there are no further shocks given to the stream, the dissolved oxygen starts recovering, because it is also in contact with the atmosphere and there is a oxygen transfer that takes place. And depending on where we are in terms of the oxygen level, these are also related with the species that can survive and so on. That is a branch called as eco-hydrology, where we also start looking at how the ecology responds to different hydrologic conditions. Now, when you are looking at any hydrologic system, there are a large number of human interventions that will impact. For example, you may have a dam here which has a reservoir. This reservoir is fed by the rainfall that falls on its own catchment, and then you are using that for hydropower generation, irrigation, etc. Then because you built a dam, the downstream of dam, it is a regulated flow, and therefore, the flow will be much smaller. The water quality becomes critical there, because you are receiving the water also from agricultural area. Imagine a rainfall that happens in these agricultural area and then starts joining the streams. It will bring in pollutants because of the fertilizers and the pesticides and so on, and it joins all along the stream. That is called as a non-point source pollution, because you cannot control that, and it happens all along the stream. Then you will also have the municipal and industrial effluents. These kind of situations are becoming extremely unfortunately common everywhere. Typically, the Ganga region, if you see in the Kanpur area, etc., this is a very common sight, and they form the point sources of pollution. And you are using this water for municipal and industrial supply, etc. You must also realize here that all these components are interrelated. There is a groundwater reservoir which also feeds into the stream, that is called as the base flow, and then you have the recharge that is happening. So, each of these component is in some sense interrelated with other components, and on top of that you have the climate change, land use change and structural interventions affecting most of these components. And that brings the challenge of how we handle the different levels of anthropogenic interventions at different scales of water systems. When we start looking at the climate change, as you know, the global temperatures are known to be increasing, and in fact, there is a collective mechanism now that has developed between the intergovernmental panels, I mean through the intergovernmental panel, that somehow you make sure that the temperature increase does not cross 2 degrees. There is a global average temperature increase with respect to the pre-industrial era. In fact, many of the smaller countries, island countries, etc., are insisting that it should not increase beyond 1.5 degrees because of some several implications there. So, the first level of risk here you see this is millions affected because of rise in temperature. So, as the temperatures start growing beyond 1.5 degrees, etc., the risk of coastal flooding obvious, because the sea levels will rise. And if your coastal areas are flat, in fact, it is said for Bangladesh and countries like that which are flat, bulk of submergence may happen because of coastal flooding. And as you cross 2 degrees, these kind of impacts will be sharply rising. Then you have the risk due to hunger because of the food production, and that again starts rising along 2 degrees. Then because the temperatures rise, you have the risk associated with vector borne diseases, and that is a major risk, the risk of malaria and other vector borne diseases. We are still talking about millions of people affected, but the most critical impact of the climate change will come through water, and water shortage is the most critical impact, and we are seeing that water shortage on this axis, which is an order of magnitude higher compared to this. As long as we are below 1.5 degrees, it is manageable still, but once we cross 2 degrees, there is a huge risk of water shortage, and therefore, the water systems become important. A good scientific understanding of the water systems become extremely important, and how the climate change affects water systems at various scales. Now, what this shows is the coastal areas. As I said, the sea levels, because of the sea level rise, how many cities will be affected, and this dots here show the relative magnitudes of the population and so on. As you can see, many of our own cities are involved in that. So, look at the climate change. There are 3 visible signals of climate change which are already in place. You can already evidence them, namely that the global average temperatures are increasing, the precipitation patterns are changing, and the sea levels are rising. Now, these have implications on a large number of hydrologic processes. Increase in temperatures, as I said, straight away has implications on the evapotranspiration, which governs the vegetative demand. Then it also has an effect on the water quality itself. But increase in temperature by itself has effect on the circulation patterns and therefore on the precipitation. So, these are all, they have their own feedbacks. Then we have change in precipitation patterns, as you are seeing in many places in India as well as outside, that what used to happen over a long period of time, the seasonal rainfall may have remained constant, but bulk of it is happening in very short spells. And that has implications on the intensity, magnitude of floods and droughts. Of course, the stream flow dictates the water availability. Rise in sea levels, inundation of coastal areas, I said, but what is less understood is, or less emphasized, is the seawater intrusion. We are already exploiting groundwater in the coastal aquifers, and therefore, there is a gradient that is created between the salt water and the fresh water. On top of this, now if the sea levels start rising, this gradient increases. So, what used to happen around 10 kilometers, 15 kilometers etc. in the coastal regions may start happening up to 20 kilometers, 25 kilometers and so on. And therefore, we need to look at the issues of concern as far as our country is concerned. Now, we depend heavily on our river systems. For example, Ganga, Brahmaputra, and then Narmada here, Kaveri, Pennar and so on. So, these are our major water sources. The first level of question that we need to ask is, how do these water systems respond to global climate signals? What happens to the flows, whether the flows are likely to go down, go up and so on. And all of these issues, for example, the frequency and magnitudes of flooding events as well as droughts, you are witnessing frequent floods, for example, the Kedarnath type of floods, Kerala type of floods, Chennai type of floods, and similarly Marathwada type of droughts. These extremes are known to be increasing, but whether they are in fact due to climate change or not is very difficult to say with the current state of knowledge. But that the patterns are visible is very clear. Then we also start looking at what is happening to the demands as well as delays in onset of monsoon and so on. So, all of these can be affected by global climate events, and it is for us to quantify these kind of impacts and then see how the water systems are likely to behave in future. When we do that, because we are standing at this point in time and want to project into the future, we have to fall recourse to the models. There is no luxury or opportunity for us to make observations in the future. So, the atmospheric scientists provide us with the projections of climate through the global climate models or the general circulation models. Now, these are physically based models and they have large number of differential equations involving physics, fluid motion, chemistry, etc. They are and they simulate all of these processes, for example, winds, the heat transfer, radiation, etc. We as hydrologists use these climate models and bring it down to our hydrologic scales. By their very nature, the global climate models, because they have to act, they have to perform at the global scales, their resolution is very large. The scales are very large, the resolution is very low, which means that they typically operate at 2 degrees, 2 degree by 2 degree or 1.5 degree by 1.5 degree, etc., 150 kilometers by 150 kilometers. That is the grid size. Whereas, as I said right at the beginning, the hydrologists have to look at very small scales because of the enormous heterogeneity that exists on the ground. The global climate models, this is an old scenario, but it is easy to explain through this, that is why I use this. When the global climate models simulate the climate into the future, they use certain type of scenarios, how the world is likely to behave in future, how the climate is likely to unfold. That will depend on the greenhouse gas emissions, how the CO2 levels are likely to increase. Now, we talk about the RCPs, that is the representative concentration pathways, but just understand that these are possible pathways in which the climate can evolve. Now, for example, if you look at let's say the entire world becomes wise and then we start behaving as good human beings and then curtail all our energy requirements and use the alternate energies, and therefore the CO2 levels will come down, etc. Then how the temperatures are likely to change, and because of such changes, such rise in temperature, how the sea levels are likely to change, etc. All of these features will be simulated by the global climate models, and those things we need to use in our hydrologic models. And when we start looking at the hydrology, then because the global climate models operate at such large scales, as I said, it may be 150 kilometers by 150 kilometers, etc. Whereas we are interested in hydrologic scales which may be of the order of 50 kilometers by 50 kilometers. Then we have vegetation, then we have topography, which will all vary within that. Then we have the societal systems that may require the information at much finer scales. So we need the downscaling techniques, that is, from larger scales we bring down the simulations to smaller scales. That is one part of the story. The other part is more important, that the global climate models, even with the current ability or current knowledge, are not able to simulate many of these variables. For example, they are very good at these variables. The GCM's ability goes from left to right. For example, you look at the working variables. These are the smooth variables, wind, temperature, air pressure, etc. They are simulated extremely well. But what we require in hydrology are the evapotranspiration, runoff, soil moisture, etc. So these are not simulated well. So we address both these issues, namely one of scale mismatch, another of variable mismatch through the downscaling, and then bring down the climate model outputs to the smaller scales. And from the climate change projections, we bring it down to the hydrologic scales. Then there are also, as I said right at the beginning, there are also other inputs, for example, topography, land use, land cover, soil characteristics, etc. All of these we can also have projections and then run our hydrologic model to look at how the water systems in a particular basin or at a particular watershed scale is likely to behave in future or the next 2 decades, 3 decades, etc. When we are doing this, there are large number of uncertainties associated with it. You quantify the uncertainties and then see whether you can evolve what we call as adaptive responses. For example, in a particular basin, on one side the supply may be going down in terms of the stream flow, on the other the demands may be going up in terms of the evapotranspiration and other demands. Therefore, the mismatch between the availability and the demands, that may be increasing. Then what can we start doing now so that the system will still be reasonably sustainable, if not better than what it is. So, I will just show you some example. Typically, you look at the Orissa region. These are the GCM grids. At each of these grids, so this is maybe about 3.75 degrees or some such thing. At each of these grids, you have the GCM simulated output available. And what we are interested in is the precipitation in this particular region. So, we develop relationships, statistical and dynamical both, between the rainfall as well as the GCM simulated other variables, and then use them and start looking at the future. As you can see, when you are around 2020, 2040, etc., most of these models, these are model scenario combinations. As you change the model, as you change the scenario, you get a different projection altogether, and that introduces a huge uncertainty. But these are the only tools that are available as of today. The GCMs and the scenarios, we use them and then project the hydrologic variable into the future. The hydrologic variable here is the drought indicator, which is converted from the precipitation. That is a standardized precipitation index, SPI, which indicates the drought. As you progress in time, these will start falling apart, and therefore, there is a huge uncertainty associated with it. How do we quantify these uncertainties? The first level of uncertainty is assume that each of them is, because of our lack of knowledge, you assume that each of these scenario that you have developed just now is equally likely, because we do not know which one is better suited for our condition. But in combining these, and then there are ways of combining and then providing probability distributions and so on. Very sophisticated methodologies are available, quantitative methodologies, and you combine all of them. But when you are combining, let us assume that one model scenario combination was actually correct, but because you combined, you killed that science there, and therefore, reducing the present knowledge about climate sensitivity to a single probability distribution would clearly misrepresent the scientific disagreement. There is a scientific disagreement between these various models and scenarios. So, we need to evolve different methodologies for this. So, what we then do is we address these uncertainties with different methods. There are two major types of uncertainties. One is the aleatory uncertainty, which is irreducible because of the natural processes, they are random processes, there is some uncertainty always associated with it, you can't do anything about it, you have to only quantify and deal with this. This is best done through probability distributions, Bayesian methods, etc. But there is another type of uncertainty which is recognized lately. This is called as the epistemic type of uncertainty, which arises essentially because of our lack of knowledge. We do not know how the socio-economic systems are likely to behave in future. That is absolutely lack of knowledge. And these are addressed through the softer type of uncertainty handling. Typically, for example, you have imprecise probabilities, possibility theory, evidence theory, etc. All of these we combine along with the Bayesian type of uncertainties and then start looking at the uncertainties associated with the climate change impacts. Now, when we do that, the first level of information that we can provide for the policy makers is not just the single valued probability distributions, but you give a bonds. So, that the bounds the maximum and minimum levels of the drought in particular region is such and such and so on. So, all of these are intricate stories. Essentially, you must understand that the uncertainties associated with the climate change impacts as far as hydrology is concerned, that is a major component of research and there is a huge potential for that. What we did with precipitation, we also do with the stream flow now. As I have been saying, the flows will dictate the water availability and then we reconstruct what are called as the flow duration curves. For example, it gives with 60% probability what is the flow that is exceeded. Now, this is the observed one and then we do that with different models and scenario. If you see that most of the model scenario combinations are indicating that the middle level flows are likely to go down in that particular river, that has implications on water availability for all our purposes. On one side, the water availability may be going down, on the other side, the requirements may be going like this. Although your seasonal water availability may go down, your flood peaks may still be increasing, because most of the water will be coming in very short spells. And all of these scenarios which are actually projected, we combine them and start looking at what happens to your human structures, how do you operate. For example, those who are following the Kerala flood story, there was an immediate response from many people that your reservoirs were not operated correctly and therefore, it exacerbated the flooding situations downstream. So, we need to start looking at how the human structures, human man-made structures are actually operated during these periods of crisis. And that is what we start looking at, that is the Hirakud reservoir that I showed. And we say that during the flood period, you need to operate it in a different manner. There is a big story there, do not worry about that, but essentially the idea is that as the projections complete with their uncertainties are available with you, you must be able to evolve adaptive responses for all of these structures. We will again come back to the evapotranspiration story. As I said, most of the climate variables will affect the evapotranspiration and therefore, the water demands. So, we must have the wherewithal or the methodology to bring down the climate projections to the scales of agriculture. For example, 2 acres, that level of scale, and then start looking at how each of these crops, for example, the paddy will respond in a different way compared to the sugarcane, compared to let us say some other millets or some such thing. So, it also depends on the type of vegetation. So, what we then do is that the climate variables that affect the evapotranspiration, namely the wind speed, the temperature, the relative humidity, radiation, etc. From the climate models, we bring it down to the smaller scales and then start relating it with the evapotranspiration. And when we do that, we see that for most of the models, this is for one model scenario combination, but for most of the models, it shows with respect to the historical data, the evapotranspiration is likely to increase. And as the evapotranspiration increases, your water requirements for all of these crops will start increasing. Now, these are again, I have given one point example here, but these are associated with uncertainties because you have to do this with several models, several scenarios until you have enough confidence in that. Then the next question is on the hydrologic extremes of floods and droughts. Typically, this one is seen every year, and this time unfortunately Pune also got huge floods, Sangli got floods, Mumbai every year it gets floods, Chennai gets floods, Bangalore gets floods. So, as time progresses, more and more cities are added to this library, and this is becoming extremely common now. There are two issues here. One is something is happening in the atmosphere because of which the rainfall intensities are increasing in the urban areas. The second is the way the cities have grown. We have mismanaged the development absolutely, and therefore, the way the cities respond to these high intensity rainfall, that has gone haywire, and therefore, we see all of such situations. Just the example of Chennai 2015 floods. It is a very tragic event because 400 people lost their life in the city, and there are people like us. Generally when floods happen elsewhere, we do not relate ourselves with that event because it happens to some other people. But Chennai, it was exactly the people, middle class people like us, who lost their lives. And it is tragic because on one side the technologies have grown significantly, and on the other side these kind of situations keep on recurring. So, these are the reasons. For example, unprecedented rain, 300 millimeters, 350 millimeters, like this day after day, huge rainfall occurred, just about 3 to 4 days. Then there were upstream reservoirs, they just released the water exactly when the city got flooded, 29,000 cusecs, cubic feet per second for 3 days. That amount of water was released just when the city has flooded. Then Adyar river was there, it was already overflowing, etc. All of these combined, they created havoc in the city. Then the question that we need to ask is, what is happening on the atmosphere and what is happening on the ground? So, it is known that the intensities of the rainfall that cause urban flooding are in fact increasing. So, we ask the question, how do this short duration high intensity rainfall respond to these global events? There is a huge scale mismatch there because one is on the spatial scales, another is on the time scales. So, we need to address these. We first start looking at how historically it has behaved. For example, over the last about 30 years, if you segregate this into two parts, one is nearer past, another is farther past, and start looking at the intensities. For example, these are the intensities, this is duration. These intensities are known to be increasing. This is farther past and this is the nearer past. So, there is a continuous increase in the intensities at these time durations. In fact, for the urban flooding, the durations of interest would be less than 1 hour, 30 minutes, 15 minutes, etc., because as I said, the flow takes really rapidly, and that has implications on the duration. Now, this does not mean that the rainfall happens only for that duration. There is a critical 15-minute period or 30-minute period when the intensities are very high, and once it starts flooding, that gets the flooding continues. So, this is what we typically do. Now, the current knowledge from the Japanese model, they bring it almost to the flat scale. So, from global scales, there are dynamic downscaling techniques that are developed. You come to the regional scale, then to urban scales, and almost to the block scale, they can bring it down. What is happening on the weather? So, there are weather models, numerical weather prediction models combined with the climate models, and then you will be able to show on real time forecasting how these blocks are likely to behave over the next few hours and 24 hours, etc. Then what we do is, this is what we did for the Bangalore city. We take a large number of climate models and take about 85 simulations. These are the climate scenarios, and then we start simulating the IDF relationships. So, with respect to the duration in hours, how the intensity is likely to increase in future. This is for the future. Because we are using climate models, the space scales, there is a mismatch. There are time scales, there is a mismatch. So, we do a lot of methodological improvements there on bringing down from larger time scales to smaller time scales. We use what are called as a scale invariance theory and stochastic disaggregation, bring it down to the smaller scales and reconstruct the IDF relationships. IDF is intensity, duration, frequency. Frequency is once in about 10 years, once in about 20 years, what kind of intensities are expected, that is the frequency. So, as you can see, these short duration intensities are likely to increase. This is from a large number of simulations, As you go to higher durations, 24 hours, etc., there is not too much of a change, then not too much of a uncertainty also. Whereas short duration intensities, which have significant implications on the urban floods, they are likely to increase. Also, you know that there is a significant spatial variations in the high intensity. I am just showing for some years, these are Bangalore and cities, IMD cities here, IMD rain gauges, how the maximum rainfall has increased over a period of time. Not increased, varied over a period of time in the city itself. As I have been saying, in IISER there may be a very high intensity of rainfall, just next door in IIT Pune it may not be happening. It is that kind of variation as far as high intensity of rainfall is concerned. And therefore, we need to start developing the spatial patterns of the high intensity rainfall which cause the floods. So, we develop these kind of things with Bayesian hierarchical models and then show which parts of the cities are likely to receive or have been receiving much higher rainfall compared to others. These have significance because if you are planning for some very critical installation, let us say nuclear power reactor or some such thing, you cannot be using the average rainfall over the city. You have to necessarily look at the spatial variation, look at where you are locating that and then see the intensity of rainfall and so on. Now, we come to slightly larger scale and start looking at how these large scale land use change have affected the hydrology of the region. So, we go to the Upper Ganga basin and start looking at what has happened over the last about 4 decades. If you know the green revolution, while it provided a very good food security, it has also changed the landscape very significantly in terms of intensification of the agriculture, and because of which over the last about 3 to 4 decades the land use has significantly changed, specifically with respect to the flood, the forests being changed to agricultural lands and so on. So, this is the type of analysis that we do. We look at various locations where it has changed. At this scale it is very difficult to appreciate, but when you look at the numbers, that is quite scary. That's the land use change that has happened over a last about 3 to 4 decades has caused significant change in the hydrology. Now, we also look at the change in the climate, and for that we have what are called as a dynamically downscaled outputs available from IIT Pune. That is a Cordex outputs. So, we on one side we look at how the land use has changed, and on the other we look at how the climate has changed and how it is likely to change in future, and then start looking at what happens to the flows of the Ganga river. And this one, do not worry about the details there. Essentially what it shows is that as the land use changes in the particular manner and as the climate changes in a particular manner, there is a significant stream flow decrease both for non-stationary and stationary conditions. We will worry about this slightly later. That means something that is changing continuously and something that is held constant with respect to the past. Now, this is the next question that we ask. Then we are talking about the Kedarnath type of floods happening 2013, 14, 15, etc. Continuously every year the same type of floods are happening, but there is hardly any data that is available, including the rainfall data. Then we fall recourse to the global data sets which are available from the satellite imageries and so on. And if you have a high resolution numerical weather prediction model, for example, the WRF, weather research and forecasting model, which draws its boundary conditions from the larger climate models, we ask the question, can we use all of these global data sets and try to reconstruct what has happened? If we are able to reconstruct, that means we are imparting knowledge onto the system, so that next time when such a situation evolves, you will be able to forecast. So, that is the question that we ask, and then we look at these. For example, Haridwar is here for your reference, then Tehri is somewhere here, number 2 is Tehri. So, this is the part that we take first, and then look at various rainfall data sets that are available from the global communities. For example, TRMM and all the satellite data sets we use, and then combine a numerical weather prediction model with the hydrologic model VIC, and then see whether by directly using the rainfall data sets we are able to predict it better, or by combining these numerical weather prediction models with the hydrologic models. So, our conclusion is that out of 5 such events, 5 peak events we chose over the 5 years, 3 we were able to simulate very accurately, that is the peak flows, or we were interested only in the peak flows. So, the peak flows that happened in that region, we were able to predict accurately by model coupling. It's only one way model coupling, that is WRF feeds into WIC. But eventually we want to do it both model coupling. That means hydrology also feeds into the weather there, local weather. So, that is the next issue that we talk. The last issue that I want to talk before concluding is one of non-stationarity induced because of the human interventions. Classically, the hydrologists or in fact any scientists, when they fit the model, you look at the historical data and then tweak your model parameters, fix the model parameters and then hold that stationary and then look into the future. The model parameters themselves are not changed. This is called as a stationarity. That means the future will be similar to the past. That is the underlying premise there. But because of so much of human interventions at all scales, the future will no longer be similar to the past. The past will no longer provide a valuable clue to the future, and therefore, it becomes non-stationary. And that is what we ask the question, that we talk about return periods. That means once in about 10 years this kind of intensity is likely to happen, 50 years this kind of, they are called as the return periods. Now, what happens to the concept of return periods itself, because that return period concept was based on the history, but history is no longer similar to the past. So, what we do is that because lack of data in India, we looked at Colombia and Colorado for droughts. So, we look at both extremes of floods as well as droughts and ask the question, the historically developed return period, how long into the future it is likely to remain constant. For example, 50-year return period of floods. As we go forward, when will it be significantly different? Whether next 10 years the 50-year return period will be different. So, this is the kind of question that we ask. And then we develop several methodologies associated with that, address the uncertainties and then show for floods whatever we said about 50 years and we designed our structures, etc. After 2036, this is likely to be much different. Similarly, for 100 years, 2073 and so on. There are a large number of details there, do not worry about that. The concept is that you do not treat these hydrologic processes as stationary any longer because of so much of human interventions that has taken place. There is a huge uncertain non-stationarity that is introduced, and there are ways and methodologies available to address these non-stationarities. Then the next question is that we have the data and then we do lot of exercises on the data, we put it onto another projection, etc. We want the data to say what we want it to say, and that is what is written here. So, this I am coming to the criminal side now. One is you torture the data, it will say what you want. The next is if there is a signal of climate change on the hydrologic processes, much as a criminal leaves the fingerprint behind of the crime, the climate change has to leave the fingerprint behind on the hydrologic processes. We capture those fingerprints and start attributing the cause. Let us say that the hydrologic change has happened and you are able to detect that there has been a change. Can you now say that this change is because of a climate change or because of so many other factors that happen? So, this is what we call as optimal fingerprinting. So, we actually capture the fingerprints on the hydrologic signatures and then isolate the fingerprints like the investigators do, like our Sherlock Holmes or Watson. You isolate, this is not because of this reason, this is not because of this reason, etc. and then say this is a graph that shows that. That means, you run your climate models and hydrologic models for different conditions. If it is only a natural variability that has caused this change, you should be able to identify that. That is, bulk of the change has come because of the natural variability alone. Then you start, if you are unable to explain by that, then you start looking at the volcanic runs, then anthropogenic force runs. Like this, different levels of sophistication you do and then isolate the signals. Actually, we look at the signal to noise ratio, signal of climate change, noise because of the natural variability. Signal to noise ratio you take and then say with certainty, if possible, that the change that you are seeing is because of climate change. In the Mahanadi case, we were unable to say unequivocally that the change that we are seeing is because of climate change. There are a large number of other issues, typically with anthropogenic interventions, land use change, etc., the factors that I talked about, they all contribute to the change that we are seeing. So, with that I close with some issues, science issues, that in summary we are seeing the human signatures in all aspects of natural processes, much more so on the hydrologic processes. And it is important for us to capture these signals and then start looking at how the hydrology of a river basin is likely to behave in future, not only on river basin, but also on smaller scales like urban scales, watershed scales, and large continental scales, peninsular region for example. So, at these scales we start looking at how the hydrology is likely to behave. In doing so, these will be the science issues. For example, you need to start accounting for non-stationary. The world has no longer been stationary now. The world will behave in a non-stationary manner. There must be methodologies or ways by which you can address then uncertainties, we should be able to quantify, reduce, and also communicate the uncertainties correctly, because of this large number of uncertainties, if you want to do any adaptive responses, unless you communicate the uncertainties correctly, it won't be. Then these are the other issues, detection and attribution, high resolution climate simulation, and then there is also a two-way feedback. For example, what we are doing on the ground also has a feedback into the atmosphere. At large scale, imagine the entire peninsular region. Let us say that you do complete deforestation. That definitely has an implication on the climate. So, there is a two-way feedback. We must quantify these kind of feedbacks. So, with that I close and thank you very much for your attention.